Hi, my wonderful student. You are welcome to another segment of Kaduna State e-learning program with chemistry. Today, we'll be looking at the topic orbitals and electronic configuration. My name is Williams Ishaku. Under this topic, we will be looking at the topic under the following content. We are going to look at the definitions of orbitals and electronic configuration. After that, we'll move to types of orbitals, then energy distribution in an orbitals. We're also going to look at how to write electronic configuration using the SPDF notations. We are going to look at the shape of S and P orbitals. The quantum numbers, these quantum numbers are what we are going to use in describing an electron. And then finally, we are going to look at the rules or principles used in assigning an electron in an orbital. Now we are going to start. Let us look at the definition of an orbital. What is an orbital? You will recall while you were in your SS1, you were told that an atom is made out of three fundamental particles. These particles consist of the proton, neutron, and electron. The proton and the neutron are found inside the nucleus of an atom, whereas the electron is found revolving around the nucleus of an atom inside something that we describe as shell. However, this shell that we have been used in writing the electronic configuration, now we are going to move to another stage of describing another room inside the shell that we call subshells, in other words, known as orbitals. Now you may want to ask, what is this word orbital? An orbital is a region or a space where we have the highest probability of locating an electron. After that one, it is also very, very important for you to understand what we mean by electronic configuration. What is electronic configuration? Electronic configuration simply means the manner in which electrons are being arranged or distributed in an atom of an element or molecule. We use that using the shell. When we say the first shell will carry a maximum of 2 electrons, the second shell will carry a maximum of 8, the other ones will carry a maximum of 8 electrons. But whenever we're talking about orbital, it's entirely different. We make use of SPDF notation. Here we go. Let us look at the types of orbitals that we have. Whenever we're talking about an orbital, we're talking about the subshells. It therefore means that inside it is more or less like you have a room, and inside that room there are other rooms inside it. So those other rooms, we describe them in chemistry as orbitals. These orbitals are 4 in number. We have them, as you can see from the table. We have the s orbital, the p orbital, the d orbital, and the f orbital. Each and every orbital stands for something. Like the s orbital stands for sharp. The p orbital represents principal. The d orbital represents diffuse, while the f orbital is representing fundamental. It's just like in that room, each and every orbital has a maximum number of electrons that it can carry. For instance, the s orbital can only carry a maximum of 2 electrons. The p orbital can carry a maximum of 6 electrons. The d orbital can carry a maximum of 10 electrons, whereas the f orbital can carry a maximum of 14 electrons. With that, you agree with me? There is a gradual increase of 4 electrons in between the orbitals. Now, the total number of orbitals in a particular energy or sublevel is limited by the formula 2n squared, where n is a variable. It could be 1, 2, 3, up to infinity. We use that one to determine the number of electrons that each and every element can carry. Now, having said that, you know, when we are talking about how to write electronic configuration, the K shell, which is represented by, when we are talking about the shells, is represented by letter small n. This small letter n, if it is 1, it therefore means that we are going to have n squared, which means n squared will now be 1 times 1, which is equals to 1. No wonder under the first shell, the K shell, we only have 1 orbital, only 1 room, in other words. Now, subsequently, you see if n is equals to 2, the number of electrons will be equals to n squared, which means 2 squared. In other words, this 2 square is the same thing as 2 times 2, which is equals to 4, which means you are going to have up to about how many rooms in that? 4 rooms. It goes like that up to the end. Now let us continue with the other aspect of the electronic configuration. Now, whenever we're talking about this, we can represent it in a tabular form for a better understanding. Take for instance, you can see from the table above, table showing the number of orbitals and electrons in the energy level. The first one, if we are talking about the first shell, like I mentioned the other time, it has only one s orbital is found at the first shell, and so therefore the total number of orbitals there is what? 1. When you come down to the number of electrons per sub level is what? 2, which means s orbital can carry a maximum of what? 2. The same thing, the maximum number of electrons per shell is going to be 2n squared, which is equals to 2 also. Now next to that, the L shell. You may want to ask, what is this K, L, M, and others? It's just that the various rooms that we have where you can locate the electron. Like in the K shell, it is represented as room 1, the L shell room 2, and subsequently like that. However, if you are talking about the L shell, there you have the 2s and the 2p orbital. Under the 2s, the total number of orbitals that are there are 4, because the 2s is 1 and the 2p are what? Are 3. That's what we call degenerate orbitals in chemistry. What is degenerate orbitals? Degenerate orbitals are orbitals that have the same energy level. Let me put it in this way. It's just like you have rooms in an upstairs, where in a particular upstairs you have similar rooms. You have up to about 3 rooms. We call that one degenerate orbital. They have the same energy level. Like the p orbitals in chemistry is 3-fold degenerate. The 5 orbitals is 5-fold degenerate, and the f orbital is 7-fold degenerate, which means they have, the other one is having 3 rooms, and the other one is having 5 rooms, and the other one is having 7 rooms. But the s orbital, only 1 room that is in it. So therefore, if you look at the M shell, you also have the 3s, the 3p, the 3d, and then the total number of electrons there will be equals to what? 9 based on that. And then the number of electrons per subshell will be equals to, for the 3s you have 2, for the 3p you have 6, for the 3d you have 10, and you have a maximum number of electrons using 2n squared for the 3 shell. If you multiply 3 times 3, that will give you 9, times that will give you what? 18. Now the n shell, you can also see we have the 4s, the 4p, the 4d, and the 4f. The total number of electron orbitals that are there are 16, based on the table you can see. And we also have the total number of electrons per sub-level. Per sub-level means per room. What is the maximum number of electrons that a room can carry? We have them, for the 4s we have 2, for the 4p we have 6, for the 4d we have 10, and F is 14, just like I've mentioned earlier. And the total maximum number of electrons that you can have there is what? 32. Energy distribution in an orbital. The orbitals are not just arranged haphazardly. They are arranged in an organized way according to their energy level. Like I mentioned earlier, we have 4 types of orbitals. As you can see, based on the energy, on their energy level, we can arrange them from 1s, 2s, 3s, 4s, 5s, 6s up to 7s. Then we go back to p. When we are getting to p, we are going to jump a line and then we start with 2p. We don't have 1p, but we start with 2p, 3p, 4p, 5p, 6p, up to 7p. We move again to 3d. We are going to jump another line again. We are coming to line 3. That will be 3d, 4d, 5d, 6d, and 7d. When we are coming to F, we jump again to the fourth line. That will be 4f, 5f, 6f, up to 7f. Now, when electrons want to enter these orbitals, they enter in a special way based on their energy level. When the first electron will enter, it will first of all enter 1s, as you can see. It implies that it will first of all enter 1s from the table, to 2s, to 2p, to 3s, to 3p, to 4s, and 3d. And each and every electron has a maximum number of electrons that it can carry. My student, don't forget that from the beginning of this lesson, I made mention that the s orbital can only carry a maximum of what? 2 electrons, while the p can carry a maximum of 6 electrons. The d can carry a maximum of 10 electrons, whereas the f can carry a maximum of 14. Now, after arranging these orbitals according to their energy level, then you begin to slot in their electrons based on the maximum number of electrons that they can carry. For example, if you are asked to write the electronic configuration of the following using the SPDF notation, the first thing to do, you know, sodium. Sodium has an atomic number 23 with atomic number 11. When we are writing an electronic configuration class, don't forget, we always use the atomic number and not the atomic mass. We use the atomic number and not the atomic mass. So, if you are going to write the electronic configuration of sodium, you look at it, you start with 1s. What is the maximum number of electrons that s can carry? Is 2. You put 1s2, you go to 2s, it has a maximum of 2 electrons to carry, you put 2. 2p, maximum of 6 electrons, which is going to give you 2p6. You go to 3s, which has a maximum of what? 2 electrons. But the electron is not enough because you have distributed 2 plus 2 plus this, that will be 10, plus the other one, that will be 1. So the 3s orbital is going to carry 1 electron. That is how to write the electronic configuration. Another example, imagine you are given an element like calcium, and they want you to write the electronic configuration using the SPDF notation. You agree with me that you start with 1s2, 2s2, because that's the maximum number of electrons that s can carry. You go to 2p6, 3s2, 3p6, and 4s2. That gives you a total of 20. Don't always forget, whenever you want to write the electronic configuration of an element, you make use of the atomic number and not the atomic mass. My student, in your exam, sometimes as simple as it might look like, they can ask you to give the shape of s and p orbital. In chemistry, we are made to understand that the shape, that is the shape of the room that is in s orbital, is spherical in shape. Some would call it oval, while that of the p orbital is a dumbbell shape, as you can see above. Whenever we have an electron, in chemistry, we have something that we use in describing this electron in an orbital. We make use of what we call quantum numbers. These quantum numbers are 4. We have the principal quantum number, the azimuthal quantum number, the magnetic quantum number, and the spin quantum number. It's just like you want to describe me. There are features that you can use in describing me as a person. So it is with electron. If you want to describe an electron, you make use of these 4 quantum numbers in describing an electron. Now I'm going to pick them one after the other and then show to you how you can use that in describing an electron. Here we go. Let us start with the principal quantum number. The principal quantum number is more or less telling us the shell in which the electron belongs to. We will make use of small letter n whenever we were talking about the principal quantum number, which is telling you that is it in shell 1 or shell 2 or shell 3. Now, we can have n could be either 1, 2, 3, or 4 up to infinity. That is the principal quantum number. Another one is the azimuthal quantum number. The azimuthal quantum number is telling us about the orbitals. We make use of the formula L is equal to n minus 1, where n, like I mentioned earlier, stands for the shell. If the element belongs to shell 2, if you subtract 2 minus 1, that will be equals to 1. And in chemistry, if your L is equals to 0, it means it is an s orbital. If it is equals to 1, it means it is a p orbital. If it is equals to 3, it is d, and if it is 4, it is f. That is how we use what we use in describing the orbital. We also have the magnetic quantum number. In a simple term, when you have so many rooms that the electrons are there, there's a way you can use in describing the number of rooms in a particular room. You know, in a house, you can have so many rooms, isn't it? Now, the various rooms that we have in a particular orbital, that gives us what we describe it, we call it angular momentum. That is the magnetic quantum number. For example, I made mention that when we are talking about the p orbital is threefold degenerate, which means it has 3 rooms in it. The d orbital is 5-fold degenerate, which means it has how many rooms in it? 5 rooms, while the f orbital has 7 rooms, that is 7-fold degenerate. What are degenerate orbitals? They are orbitals of the same energy level. The last but not the least is the spin quantum number. The spin quantum number is telling us the direction of the electron. Sometimes the electron could be looking upright, and other time it could be pointing downward. When it is pointing upright, when we want to describe the orientation of that electron, we use +½ If it is pointing downward, we make use of -½ in describing the position of that very electron. Now, my students, these are what we use in describing an electron. Now, whenever we are assigning an electron in an orbital, we are being guided by 3 major principles or rules. The first one is the Aufbau principle. What is Aufbau principle saying? Aufbau is saying that electron will occupy the lowest energy level first before moving to higher energy level. You can see here we have 1s. They will first of all occupy 1s before moving to what? 2s. They cannot jump 1s to 3s. That is what Aufbau is saying. Next, we have another scientist that has given us his own rule. We call it Hund's rule. He is also saying that electron will occupy degenerate orbitals singly before pairing begins. What that one means is that the orbital will first of all enter, if we have a degenerate orbital like the p orbital, the p orbital is having 3 rooms. We have the 2px, 2py, and the 2pz. They will first of all enter 1, 1, 1 before they will come and start pairing. There is no way they can just start pairing from 2px and they will start pairing. They will first of all enter 1, 1, 1 before they will come and start pairing. That is what that rule is saying. Next to that is what we call Pauli's exclusive principle. And what is this principle saying? It's saying that no 2 electrons in an atom of an element will have the same set of 4 quantum numbers. What that one means, there is no magic whatsoever that whenever you are describing an electron, that they will have the same set of 4 quantum number. These 4 set of 4 quantum numbers that I've mentioned, the principal quantum number, the azimuthal, another name for azimuthal is subsidiary. So don't get confused if they are talking about subsidiary quantum number instead of azimuthal quantum number. There is no magic whatsoever that 2 electrons will have the same set of 4 quantum number. Thank you, my student. I believe you have learned a lot. May I, at this juncture, invite my able colleague, Mr. Ibrahim Omar, to come forward for the summary and the assignment. See you another time. Stay safe and remain focused while you learn. Thank you.
Good day, my wonderful students. I'm here to give you a brief summary of the lesson presented by my able colleague, Mr. Williams, on orbitals and electronic configuration. He started by defining orbitals and electronic configuration, and he defined orbital to be a region or space in which we have the highest probability of locating an electron. An orbital is said to be a region or a space where we have the highest probability of locating an electron. Then electronic configuration has to do with the distribution of electrons in the orbitals and shells of an atom. Electronic configuration has to do with distribution of an electron or of electrons in the shells of an atom. Then he made mention that we have types of orbitals, which he categorically states 4 types of orbitals. He said we have the s orbital, the p orbital, the d orbital, and the f orbital. The s orbital, also called the sharp orbital, can accommodate the maximum of 2 electrons. Then we have the p orbital, which is called diffuse, which can accommodate the maximum of, the p orbital principal can accommodate the maximum of 6 electrons. The d orbital, which is diffuse, can accommodate the maximum of 10 electrons, while the f, which is the fundamental, can accommodate the maximum of 14 electrons. After that, he moves to energy distribution, in which he states that the energy with the orbital with the least energy is 1s, followed by 2s, then 2p, 3s, 3p, 4s, then 3d, and so on. Then he made mention that the shape of the s orbital is spherical, that is a circular shape, while the p orbital is dumbbell, and dumbbell, you can take of it as a kind of a sign of infinity in mathematics, a big sign of infinity. Then also he moved to quantum numbers, and he said in chemistry we have 4 sets of quantum numbers. The first quantum number is the principal quantum number, represented by n, and it has the it defines, or it tells you the number of shell, or the shell in which an element is located. When n is equals to 1, then it is in the first shell. When n is 2, then it is in the second shell, and so on. Then we'll go to the second quantum number, which is the subsidiary quantum number, or azimuthal quantum number, which determines the number of subshells which an element is located in. Then the next one is the magnetic quantum number, which is represented by small letter m, and it determines the number of orbitals in a subshell. Then finally, we have the spin quantum number, which determines the orientation of an electron in an orbital of a shell. Having said that, then he moves to rules that are used in assigning quantum numbers to an orbital. Then he talked about the Aufbau's principle. The Aufbau principle, which is the building up principle, states that if electrons goes into orbitals, it accommodates the orbitals with the least energy before it moves to the energy with the orbitals with the higher energy. Then the Hund's rule said that when electrons occupies the generate orbitals, that are orbitals of the same energy, then they do that singly before pairing will start. And then finally, the Pauli exclusive principle said no set of quantum number, or no element will have the same set of quantum numbers. That means if we have two electrons and then we are defining their quantum number, they cannot have the same set of 4 quantum numbers. It is very important to note that if they occupy the same orbital, then it means that the spin, one will be spinning up, the other one will be spinning down. That is to say, the quantum numbers can never be the same. Having said that, I will give you an assignment to see if the learning have taken place. And then in the assignment, we have question 1. Question 1 says, what is an orbital? Question 1a, what is an orbital? Question 1b, state the maximum number of electrons that the 3D orbitals can carry. I'll take 1b again. State the maximum number of electrons that the 3D orbital can carry. Then question 2, write the electronic configuration of the following using the SPDF notation. 1, aluminium with atomic mass 27, atomic number 13. Roman figure 2, sodium, atomic number 23, atomic mass 23, atomic number 11. 3, potassium, atomic mass 39, atomic number 19. And then 4, chlorine, atomic mass 35.5, atomic number 17. Question 3. List 4 sets of quantum numbers that can be used in describing an electron. 3b. State the following rules or principles that can be used in assigning an electron. 1. Aufbau principle. 2. Hund's rule. And 3. Pauli's exclusive principle. My students, having gone this far, I will give you a set of reference materials, which are: 1. You can contact Understanding Chemistry by Godwin O. Ojokuku, or at Senior Secondary Chemistry by S.T. Baja. If you have any problem, complaint, questions, or you want to submit assignments, you can contact us using these numbers: Williams Ishaku 081-606-70920, or of course you can call Mr. Philip Mammon 080-2659-8861, or Ibrahim Umar 070-3620-2842. Stay safe, stay home, and keep learning. Thank you very much.